Welcome to Beyond the Qubit. My name is Frank Dekker, and today I have a special guest, Olivier Ezratty. I'm really excited for today, and the main reason why I'm excited is that Olivier is an example for me. I've read a lot of research about quantum technology, and one of the best pieces is understanding quantum technology. And Olivier, he writes a 1500-page report every year. And the best part is it's very high quality and it's accessible for free. And Olivier is very well involved with the quantum technology value chain. And what I also like in his research is that he's calling the hypes. And also if things are not real or are fake claims, he's really pointing that out. The combination for me makes it really valuable. So thank you, Olivier, for being here in the podcast. I want to read out a sentence about if a quantum computer works or not. So let me read it, and I would love to hear your perspective. A qubit is not a bit with uncertainty. It's fragile, a physical state. You cannot read it without destroying it. You cannot copy it. You cannot directly inspect what it contains. You can never ask a qubit a question. Instead, you prepare a physical system, let it evolve under careful designed control pulses, and then force a measurement. You obtain a single outcome, and that outcome is not an answer but a sample. The qubit does not reason or choose. It simply reacts to physical forces and then collapses. Seen this way, what we call quantum computation looks less like a direct computation and more like a system dominated by migration and interference rather than control. So my question is this: do you believe that a large-scale quantum computer will work in the engineering sense, meaning stable, reproducible, and convergent behavior, without redefining what we mean by computation? Or is quantum computing fundamentally a process of statistical interference, of collapsing physical systems, whose usefulness depends on accepting a different, weaker notion of computation?
There's a lot in your question. I could take one sentence after the other and
yes, please,
and fact check that, but not the whole thing. Yeah, you ask very interesting question about what's the nature of quantum computing. Let me rephrase that in a couple of ways. One is I believe that there's some determinism in the way you do quantum computing when you don't measure anything. So if you don't measure anything, it's kind of determinism. You can manage the state of your system in a semi-deterministic way. And indeed, when you do measurement in the end, you get some statistical outcome. So when you do so-called unitary transformation, so you do gates, quantum gates on your system, it's kind of more or less determinist in the way it works. And so people sometimes, they want to have some non-determinism in their code. So for example, when they do a Monte Carlo simulation, they need to embed some non-determinism. So they can use the code and some measurement to drive the generation of some random numbers, and then they use that in the Monte Carlo simulation. But if you run a typical quantum algorithm like a QPE or quantum phase estimate to compute the energy of many body system, to compute the electronic structure of some molecule, the inside of your code is deterministic. That's the outcome in the end, which is not, because when you do measure a qubit, you land into a non-deterministic thing. So controlling the qubit when you don't measure it is one of the most complex things, because there's noise, So there's noise affecting the qubit. Noise is coming from the qubit themselves, like spontaneous emission. Let's say you excite an atom to a Rydberg level, which is the one of the qubit. Instead of spontaneously, the atom will get de-excited. So with so-called spontaneous emission, it's the same for a superconducting qubit. When you excite a superconducting qubit to the level 1, it will spontaneously get back on 0. So it's one of the, I would say, source of noise. And then there are external source of noise like electromagnetic waves, heat, gravity, or many other phenomena like crosstalk and stuff like that. So there are many ways to disturb a qubit. So physicists work on avoiding the disturbance on the qubit themselves, from inside or from the outside. And then they use error correction to mitigate that problem. The bet and the guess is that with error correction, we'll make the qubit live a longer life so that it accommodates with the length of your circuit and the length of your algorithm. So that's the way it works. There are many ways to believe that it can work and many ways to believe it couldn't work. So you have a big opposition between different scientists in that field. So that's my quick answer to your question.
And maybe taking a step back, is quantum computer really a computer in the traditional sense?
Well, it depends on the way you define computing. Usually, computing is defined as a system that solves a problem with a series of instructions, data, and which yields an output. It's a kind of very simplistic way to define computing. So if you take a gate-based quantum computer, like the ones you have with IBM and the Candela and the IQM and others, we can define this still as a computer because it takes a series of instructions and in the end you get some results. And the instruction contains the data. I would say that in the classification of computing methods, there are two big particularities of quantum computing using that mode. One is that we are using a so-called process that is named in-memory processing, which is not commonplace in classical computing. The equivalent in classical computing are neuromorphic networks or synaptic networks, where the data is in the system. So you have a memory, which are the qubits, and you manipulate the memory. When in the classical sense of classical computing, you use the Chern-Neumann model, where there is a separation between the memory and the computing. So in a classical computer, you have so-called arithmetic logical units in a CPU, and they are manipulating data that comes from outside. And the hierarchy of memory in the classical computing. So you've got a CPU, it's got registers, first level, then cache memory, second level, then you've got RAM, the random access memory, third or fourth level, and then you've got storage, SSD, whatever. So you've got multiple layers of memory, and the system is manipulating the data from one level to the other. It's a hierarchy of memory, and there's the computing just managing registers. And large registers in the case of GPU, which are a capability to memorize a matrix, for example, so to be more efficient. In the case of quantum computing, it's totally different because the computing is done in the memory. Mm-hmm. The memory is the sets of qubits that you connect with each other. And so you have a memory, these are the qubits, and you connect them with gates, single qubit gates and 2 qubit gates, so you manipulate the data in the memory. And so as a result, the big difference, which may happen in classical computing, but it's not very commonplace, the big difference is you have to how do you input the data? How do you put data in your circuit? So the data is in the code. It's not, oh, I'm going to take some data here and I copy it there, like you do in a classical system. So the data is using so-called vector encoding method or amplitude encoding. So it's a series of gates that you apply on the qubits to put some data in the qubit. So that's a big difference.
Sorry, what pops up in my head is then, how do you move the data? So now, if it's in memory, it doesn't mean that you don't have to move it because it's already there. So normally with AI, with HBM and with SRAM, and now with KV caching, okay, you need to move the data and then you bring it closer to the GPU. And that causes heat issues.
Yes. So in the case of classical computing, you move the data, but the data you copy, you can copy it independently from the source. So if you take some, let's say you have a program is a series of instructions.
It causes latency and heat.
Yeah, there's latency and heat, but you don't destroy the data you copy. You copy it independently from the source. In the case of computing, you can't copy data. You can only move it. So if you move the data, you lose the source, because of the so-called no-cloning theorem. The only way to copy the data independently is to recreate it with the instruction that you were used to create the data. So let's say you have a vector state that contains some data. The vector state has been created with a series of gates applied on multiple qubits. So if you reproduce the series of gates which create the data, you can copy the data, because you recreate the data from the beginning. It's a way to create two independent sets with the same data, the same vector state. But you can't take an unknown state and copy it on a different set of qubits independently from the source. You can't do that. You can only do so-called teleportation. You can teleport some data from one place to the other. So it creates some limitations on what you can do. So the first particularity is this. No-cloning theorem. You put data in a system with executing a series of operations, gates. And the other particularity is when you measure the state of your qubits, you get a random result. I like it because it's like humor. You say, okay, I'm doing all these things, and at the end you get a random result. So why are you doing all these things? So what you do is you execute your code, you input the data multiple times. The average, more or less, the average of your computing is going to yield an interesting result. But one result is not going to be enough. You need to do that multiple times. So, for example, when you want to compute, you want to do some chemical simulation. You want to compute a ground state, so the energy, the lowest energy level of your system. You will do that thousands of times. You will do the average, and that's going to yield the valuable result. So there's a probabilistic aspect in quantum computing. So in memory, processing, no cloning, and statistical output, and averaging the statistical output, these are the three key differences compared to classical systems. But people are still working on trying to build quantum memories.
So how does that work then, Olivier?
So we need to understand why people are doing that and how they could do it, because it doesn't work yet. There are some algorithms called oracle-based algorithms, like the Grover algorithm, the Deutsch-Jozsa, the Simon algorithms. These are algorithms which are based on having a kind of black box. And this black box is yielding zeros or one, depending on polling some block of data or whatever. And so some of these oracles could ask the question to classical data. So in that case, you need a quantum memory that is able to access classical data and turn it into quantum data and create superposition. This black box is called a quantum memory. The precise name is QRAM, Quantum Random Access Memory. But nobody is able to do that right now. Nobody has tested that with more than a couple of qubits. So it's supposed to be a tool to access a big database of classical data. But if you look at the details of how it works, it doesn't scale very well. But nobody has done it physically at scale. So it's still an open question. How could we build an oracle based on some QRAM to access classical data to make it possible to run the Deutsch-Jozsa or the Simon or the Grover algorithm? So at this point in time, most of the people who would try to design oracle-based algorithms, they design a circuit based on gates, quantum gates, but not accessing classical data, as far as I know.
I'm not familiar enough to say something meaningful.
Yeah, it's complicated. There are other ways where there are other places where you need a quantum memory. It's more for quantum communication. Because when you connect, when you use so-called QKD, so quantum key distribution, if you create a key using entanglement, and you want to do that over a long distance, you need to have relays. Because the power of the photons decrease over the distance. So you need to have relays. If you want to have relays which are working with untangled keys, you need to have relays who do a kind of swap of keys, so entanglement swap. This entanglement swap works only if you have some quantum memory buffer, because there's a synchronization problem between the emitter and the receiver. So you need a quantum memory that's able to store a state of a qubit for some time, dozens of microseconds, I think. And there are companies working on those memories, like WeLink in France is working on that. A company co-founded by Hélène Diamanti, who I mentioned before. So a memory is useful for that thing. So a quantum repeater, for sharing entanglement over a long distance, you need this memory. It's a very long, short-time memory. Usually it's based on atoms that are in vacuum, and the atoms are able to store a quantum state for some time, and then you retrieve with the laser the state of the atoms, and you can store some quantum data, quantum state of a single qubit for some time on those systems.
Olivier, one of the things by interviewing the quantum technology companies, I think the things they're working on will impact AI, but the other way around also. For example, when my first interview was with Quix Quantum, and they explained that they had specific materials, silicon nitride, and they had lower errors for photonic quantum computing. But with the whole move now to co-packaged optics for scale out, and maybe in a few years' time also for scale up, those things influence each other. And now with the crazy memory prices in HBM, we also see memory innovation, like SRAM and also KV.
Yeah, sure. Speed memory.
And so of those developments, AI influencing. So the more scale there is in AI, that now is really moving the transition from copper to light. And optical is, the scale out is now moving towards optical, and maybe in 2031, it's moving also, the scale up is moving to optical. If there is much more volume, the unit costs come down. And it could enable new things. But then the other way around also, if you look at for example, Delft circuit and the interconnect that they have on the cables and the cryostat, the cryostat computing, that enables things. What do you see from your perspective? What are the most important examples that you see for the coming 5 years? You say, well, those developments in quantum will really accelerate AI, and those developments in AI will really accelerate quantum. Are there certain things that come up to you?
Well, I happen to have co-authored a paper from EU scientists on that topic. It was a kind of perspective paper which was published on Archive in May. It was perspective on AI and quantum. And what we found out is there was an existing, I would say, legacy in the way AI is helping quantum, and some promises on quantum helping AI, but still unfulfilled, I would say. So let me talk about those two things. And maybe the third one, which is photonic and AI, which is not quantum. AI is all over the place in quantum physics and quantum technology nowadays. So you use machine learning for calibration, for quantum error mitigation, for error correction, for error syndrome detection. There are many, many ways to use AI and machine learning in developing quantum technologies. So this is a fact. I mean, it works. Sometimes it doesn't scale very well to large system size, but still it's being very helpful. And of course, on top of that, you use LLMs, LLM-based chatbot to learn, to develop code, to develop even error correction codes. I know people who develop error correction codes with LLMs. Sometimes even circuit code synthesis is getting the help of LLMs. I've seen many papers on that in that field. So machine learning helps quantum definitively. The other way around is unsure, I would say, at least. There are a lot of people who are trying to develop machine learning algorithms on quantum computers, with quantum computers, and they are facing 2 or 3 difficulties. One is that usually machine learning is fed with a significant amount of data, and we discussed that before. Feeding the system with data is costly. So you may find some advantage with using quantum systems to do machine learning, but it's offset by the cost of inputting the data. There's a lack of theoretical proof that it brings a quantum advantage in many cases. So it's still a fuzzy open field, I would say.
That one I understand. Quantum is not good for big data. But on quantum mechanic effects, so for example, a cadence or a synopsis, doing quantum simulations on quantum mechanical or physical effects, they could help to simulate or improve the GPU, the heat and the latency.
Yeah, I see what you mean. Yeah, I see more potential with optical computing, which is not quantum. There are companies who are trying to develop the optical computing systems, which may reduce the energetic cost of classical AI. There are many startups there, but they are facing a couple challenges. One is they are small, usually, not well funded. The second is they need to create their own software ecosystem to be striving, and it's difficult when you are in a niche market. And there's another one, which is the difficulty to manage the training of the systems, because usually you need to do a classical training of the optical system. It's a complicated software stack to create. So it's promising when you look at the promises from many of these companies. It says, oh, we're going to save 3 orders of magnitude of energy for inferences, but then you need to do the training. It's still complicated to build those systems, but it's not the quantum world. It's a so-called unconventional computing world. Which, by the way, I have a section in my book because I cover those weird technologies like thermodynamical computing, reversible computing, superconducting computing, optical computing, even chemical-based computing, which are unconventional computing, which is not classical but not quantum. It's in between. So it's a very fragmented market with many, many different players. They don't reach a critical scale with funding the software ecosystem. That's why it's challenging for them, but it's still promising. So we'll see what happens there.
Olivier, what are you looking for to decide which quantum technology will win? Because when I look at it, there are close to 7 technologies competing, maybe even more. I find it really difficult in this point of time to decide which technology wins. So how do you look at that?
Well, it will be presumptuous to be able to define who's going to win. Most people who decide who's going to win are the people in a given technology. So they say mine is going to win and the others will lose. Like Jeremy O'Brien from Psychotom, he says, I've got the only one which can work. My machine is going to cost 1 billion and the others will lose. Okay, maybe. He's maybe right. But no, when you look from the outside, you can't decide who's going to win. It's an open research question, open academic question, open technology question. It's a mix of academic and it's a mix of science and engineering uncertainty. What I do on my own, and particularly when I update my book, is I look at the characteristic and the challenges of each of these technology options. And there are so many challenges in each of them that you can't decide, because solving the challenges is an open question. So you need to be honest about the challenges. And when you're honest about the challenges, you say, oh, it's going to be difficult everywhere. I don't say it's not possible, but it's very difficult in all cases. So if you take photonic systems, they have losses. So how do you reduce losses? Okay, there are ways to reduce losses, but not to zero. So how do you make sure that the losses are taken into account so that the computing succeeds in the end? In superconducting qubits, you have noise, a small lifetime for the qubit. You have good fidelities nowadays, but how do you scale that? Will you sustain the fidelities you have at small scale, like what IBM is doing with 156 or 20 qubits? How do you sustain the fidelities when you have thousands of physical qubits? There's no proof that you will sustain the fidelities they have right now when you increase the number of physical qubits. So that's why IBM, well, there are two choices there. Google is trying to extend the number of physical qubits per chip, Colab as well with John Martinez. So they want to go up to 10K or 20K physical qubits per chip. It's very challenging because you have a variability within the chip and between chips, and it's very hard to sustain good fidelity at scale. Then you have crosstalk noise, various source of noise at scale, which are problematic. So IBM, they chose a different way, different path. They said, okay, it's going to be difficult to scale in, so with the number of physical qubits per chip, so we're going to have multiple chips and we connect them together. Okay. Then you move the needle into how do you connect the systems, the chips. And so you need to have flexibles or whatever.
And either you say we connect the chips together, do you mean chiplets? Or do you mean scale out?
There are many ways to connect the chips. So you use chiplet when you have multiple chips on the same chiplet, like Rigetti is doing and IBM is willing to do. So, but then the connectivity between the chip is, I would say, neck to neck. So the chips are very next to the other, but still you have indium bumps and TSVs and different ways to connect the chips together. So different technology challenges. But then you are limited in the size of your chiplet. And then you connect the chiplets with each other. And then you need flexible cables. So that's what Delft Circuit is doing in Delft, so creating flexibles. Usually Delft Circuit is doing flexibles to control the chip, so to send a signal that controls the qubits. But they may do waveguides on these flexibles, which are connecting chips with each other, not just the control electronics with the chip. IBM is doing that. They seem to get fairly good results in the 2-qubit gate they do across multiple chips using flexibles, but it's still challenging. And then there's another way to proceed, which is using transduction, converting the microwave signals that controls the chip into photonic optical photons, which are easier to transport on a long distance. And that's what QFox, again, in Delft is trying to do with Simon Grossbacher, but it's complicated because there's a lot of losses there. So the success of transduction is very low. So that's very complicated to put in place. I mean, scaling out with connecting multiple chips together brings its own challenges, and scaling in with larger chips has its own challenges. So I'd say it's unsolved yet. So it's research and engineering. We'll see in the future. We have atoms and ions. They are the same. That's what people say. So same atoms, God-given, so kind of God-given atoms. Okay, fine. But the problem is that the signals you send on them is not God-given. It's laser or microwave or whatever, and there's variability in the signals that controls the atoms. And the optical systems that control the coordinates or the electronic systems that control the ions, they have a lot of variability, and that's where the noise comes from. And then you just move the problem elsewhere. So ions and atoms, they have their own challenges to scale. And interestingly, by the way, there's something I figure out when comparing the roadmaps and looking at the challenges. If you look at the recent papers published on cold atoms, you see experiments where Caltech controls 6,100 atoms. It's a lot, 6,000. In Germany, there's some experiment at, I forgot where exactly, but MPQ, maybe in Munich, they control 10,000 atoms. There was even an experiment in the US saying, oh, we can control up to 1 million atoms with some optical nanophotonic device. Okay, but when you look at the experiment, they could indeed position the atoms, but it doesn't mean they implemented the gates on these atoms. So there's always a subtlety between positioning the atoms and having local control to control single and 2 qubit gates. So there's a trick that Michel Lukin in Harvard is implementing, and QRAM is having this in their roadmap. They say, okay, it may be complicated to implement 2 qubit gates on a local basis. So what they do is they move pairs of atoms in a single place, and then they illuminate that with a single laser, which creates a Rydberg state for all these pairs of atoms. And it creates a C0 gate, let's say a CZ or C0 gate, a 2 qubit gate, on all these pairs of atoms in a given place, but without local control. You just move the atom in some place, you limit them with a single laser and the good optics, and then you move back the atom where they were before. So as a result, you have non-local control to do a C0 gate on multiple pairs of C0. It works well. But the problem is you move the atoms in that zone and back in the storage zone, and you lose the atoms along the way because it's not perfect. So, okay, there's always a solution, but there's always a problem with the solution. That's it. So it's a chicken and egg problem. You solve the problem with the solution brings its own problem, and then you have to fix the problem, and it's endless. So that's why it's complicated. And ions is the same.
Those bottlenecks, I think.
Yeah, that's the fun of science. You look at the problem, you look at the solution, you know the problems coming from the solution, and then it goes on. So let's say take IonQ. So IonQ, they knew they couldn't scale with their 1D arrays of ions with their original technology. And so that's why they acquired the British company called Oxford Ionics in June last year. Okay, so what is OI doing? OI is controlling the gates with microwave pulses coming from a circuit, coupled to some kind of magnetic gradient field that's local or global. It depends on the technology because they have the competitors doing the same. And so they're just moving the problem in elsewhere. They're moving the problem onto how do you manage the gradient field and the microwave field to control the gate. They are very good 2 qubit gates right now. They implemented a 2 qubit gate with 4 nines of fidelity, so 99.99% fidelity. It's very good. But they did that, I think it was in September, with only 2 ions. So the $1 billion question is, it works with 2 ions, but is it going to work with 200 or 2,000? Nobody knows, because we are waiting for the next chip, which is the 256 chip supposedly being released, to be released before the end of this year. I don't say it's going to work or it's not going to work. I say, show me the chip, show me the fidelities you have with 256, and we'll see that. But the laws of physics, the laws of quantum physics say that as you grow the system, the pain grows as well. So we'll see. We'll see the weight of the pain as you grow the number of physical qubits. But I'm sure, any physicist who I happen to know say, if you move from 2 qubit to 256 qubit, you're going to have some pain somewhere. And what's the weight of the pain is the question. So if, for example, as they grow the number of physical qubits, they move from 4 nines to 3 nines, it's going to be good news. Because succeeding in having 3 nines at scale is already good news. But if it's only 2 nines, then it's not good news. That's why all the investors in IonQ on the NASDAQ, they are waiting for these results. But we need to have very good audited scientific results with characterization with the new chip. So there's so many open questions everywhere. I mean, all over the place you have open questions. Electron spin qubits in silicon. I like the technology because potentially it could scale very well. The qubits are smaller, they are fast. You use CMOS fabrication lines to create those qubits. Okay. That's what Cobley, Dirac, Quantum Motion in the UK, Intel, Arke, Semicon in Finland, all these companies are trying to do the same stuff. Groove Quantum in Delft.
I interviewed the CTO, Nico.
Okay, so they all try to do the same stuff. The only problem is so far they have not succeeded in having more than 6 to 12 functional qubits with all the gates. Because it's hard at the physics level. It's hard to control the charge noise that affects the qubit. It's hard to control single electrons in their potential whale. It's hard. I will never say it can't work, but it's hard. It's very hard.
Well, I'm fascinated by, for example, by Intel, by the advantages that they have. Now they have their own foundry.
Yes.
And when they go to 14A with high-NA EUV, and the advanced packaging, I think it will be difficult for other spin qubits to compete with that. But I don't know.
Has it paid off so far? I'm not sure.
Neither do I.
No, if you look at the results from Intel, they are not that good.
Okay.
And actually, it depends on, of course, the manufacturing plant you have, but how can it be dedicated to the process? You need a special so-called PDK, so product development kit. You need to develop, I forgot what it means, by the way, PDK. It's everything that specifies what you want to put in place in manufacturing when you design your chip. You need a specific process because you need SOI wafers. You need a purified silicon 28 wafers because you need to avoid to have spin noise on your qubits. And so far, maybe I'm going to be chauvinistic here, but what Cobley has been trying to do with ST Micro in Grenoble seems to be interesting because they dedicated a specific process to handle all of that, but we're still keeping the quality of CMOS manufacturing line. This seems to have good results, but not yet good enough to say, oh, we have hundreds of qubits and it works. So it's still at the physics level and manufacturing level right now.
What do you think is more important? That there's an ecosystem of materials like Soitec, or that you have the manufacturing capability in advanced packaging like an Intel?
Everything. You need everything. Packaging, I mean, no, advanced packaging is when you do 3D packaging, chip bonding stuff.
Yeah, like hybrid bonding from conductors.
But Intel is not the only one mastering that. So I wouldn't say the Intel has a leading edge.
Those machines, like high-NA EUV or hybrid bonding, those machines are really expensive. So for a normal startup to get access to those and the miniaturization, it might make a difference.
Yes, but I have mixed feelings about that. I look at the results from IMEC, for example, in Belgium. Yeah. Chris de Greve has been experimenting many different processes using the latest EUV lithography, high resolution lithography down to 13 nanometer. That's the EUV resolution. They're using the best machines in the world. And that team has been trying to improve the process with both silicon qubits and superconducting qubits. But so far, they have not fared much better than more classical academic fabs in those two fields. So manufacturing is important, but I think that understanding the physics and the quality of the materials is still very important. And there are two different avenues with superconducting qubits and silicon qubits. But in superconducting qubits, it was amazing. The results from Chris de Greve, it were good on variability. I think they had a lower variability than the academic fabs, the ones from Rigetti, Google, IBM, and others. IBM moved its fab from Yorkton 8, which I happened to have visited 2 years ago, up to Albany in New York State. They use 300 millimeters wafers. They improved the quality of their chips with moving to a kind of upscale manufacturing plant, but not to a situation where you have 3 nines in superconducting fidelities. So, and with silicon qubits, wait and see. I would say you need to have a lot of experiments, a lot of good design, a lot of good quality in the materials. I don't have the magic recipe to succeed in those qubits. It's going to take a lot of experiment, a lot of time. So far, the ST Micro production line with Kobli is yielding interesting results, but still at a low level. I mean, they're counting electrons, making sure the electrons are in the right place. They can create interaction with the electrons, but they don't have, I would say, two qubit and single qubit gate level experiments. It's still very low level at the physics level. Same for Delft and TNO and the folks from Wolf Quantum. They don't have yet, I would say, production grade experiments with qubit gates that are safe at scale. There's a lot of work going on there.
Sometimes I'm just fantasizing like, what would be possible if a startup would have had access to that. What would have been possible? But to your point, that sometimes when I interviewed Jan Goets from IQM, he said, look, we are really a small company, not small, but because they may be the largest superconducting company for Europe. But he said, it's very important that you are entrepreneurial. And some companies like IBM and Google, they might have more bureaucratic processes, and we might be able to go faster and by taking more risk.
Yes. But what I can tell you, based on my observation on the roadmaps and the companies and the evolutions in manufacturing and so on, is whatever the roadmaps from all these vendors, the cycling between designing, manufacturing, characterizing, and testing and integrating all those chips is always longer than anticipated. Always. So if you see a company that say, I'm going to multiply by 10 every year the number of physical qubits, whether it's IonQ, IQM, whoever, it's going to be 3 times longer usually than planned. My experience is just looking at what happened in the past. Let's take Google. Google is a well-tooled company. They did create their own fab, like Rigetti and IBM. It took them 5 years to multiply by 2 the number of physical qubits.
But
5 years.
Push back on that. Google is not a hardware company. In its DNA, it's a software company.
No, but they did invest what's needed to hardware. IBM was the same. IBM, in 2018, when I started, they already have between 50 and 60 qubits tested. Now they have 120, down from 1100 with Condor 2 years ago. But it was using a technology that was not scalable because they didn't have tunable couplers. They had very bad fidelity, so 2% to 4% error rates for 2 qubit gates. So they stopped doing this. They moved back with Heron with tunable couplers. And then they moved back to nearest neighbor connectivity with the so-called Nighthawk. But they are back on 120. And 120 is the double of what they had 8 years ago in experiments. So it shows that scaling the number of physical qubits is not that easy in that case. Ions is the same. I remember IonQ in 2018, the year I started, 8 years ago, they said that they were to manufacture a chip with 128 to 129 qubits, physical qubits, for memory. And they said there are 79 physical qubits for computing. That's what they said 8 years ago. What do they have in store right now? Without the OI acquisition, they have 64 in production, but with not very well characterized fidelities. And they say they sold a 100 physical qubit system to Koreans, I think. But they're even not sure if they're going to deliver the old technology, the 1D technology, or the OI technology if it works. They even are not sure about it. So Rigetti 8 years ago, they said they had 128 in store. What do they have right now? It's 84. And with very shitty fidelities, 99.5 in base case. So scaling is very hard, and for everybody, scaling is very hard. So when you look at the paper from Pinnacle, the Pinnacle paper from Iceberg Quantum from Australia from last week, saying, oh, we're going to move from 1 million to 100,000 physical qubit to break RSA 2048. Okay, fine. Looking at the details, the 100K physical qubit to do this requires more than 1 month of computing. If you want to have 1 day to 1 week of computing, you need 471K physical qubit with very fast qubits. If you look at trapped ions and cold atoms, which are slow, you will need millions of them, millions of physical qubits. Okay, but all this is, what is it showing? It's showing that if you improve error correction based on some physical assumption on the connectivity of the physical qubit, you can reduce the number of physical qubits you need to do that. But meanwhile, the speed at which we increase the number of physical qubits that are very good fidelities, at 339 of fidelities, is very slow. So whatever happens, you improve the resource estimates based on some hardware assumptions. But if you look at the pace at which the hardware is progressing, is not as fast as what people would like it to be. So hardware is still the bottleneck to scale.
In that, I like to study the interconnect for the scale up and for the scale out, but also the error correction ratios. I want to talk about your energy initiative and about quantum error correction. Where should we start? You can
QEI first. Yeah.
Could you maybe explain where you're working on and what you want to achieve?
Well, the QEI was built 4 years ago with my co-founders based on the belief that we should look at the energy consumption as the technology is being designed, not as an afterthought. More or less like what's happening right now with AI, even though I don't believe AI people are just bad guys. I mean, the growth of AI has been crazy thanks to LLM, so the problem gets bigger. But people in AI, particularly the guys from NVIDIA, they still improve the energy efficiency of their chips over time. Each new generation is more energy efficient thanks to what TSMC is doing in manufacturing and increasing the density, even though density is not increasing that much, but okay. So we thought that it was good to look at the problem earlier. That's the belief, the idea. To do that, you need multiple things. One is you need to raise the awareness of the topic itself. So that was one of the goals of the QI, saying that's an issue. You should look at this now, not later. The second is you need to create a kind of new approach with the topic, which requires a lot of interdisciplinary and transdisciplinary scientific and technology approach. So you need to have multiple people talking with each other. And it takes time. It's not obvious. So usually the large companies, they do that internally, like IBM and others. They are interested in the topic, they do it internally. But what we want to do with the QEI is to do it outside the company. So between academic teams, having error correction people, software people, talk to physics people, talk to the engineering, enabling tech, many of them being in the Netherlands. I mean, with DevCircuit, QBlocks, OrangeQS, QFox, many companies play a key role here in the Netherlands where you are. The third one is how do you measure, how do you evaluate those things? That's why out of the QEI, we created a group, a standardization group at the IEEE, based in the US. And we have a working group for the QEI looking at how do you evaluate the energy consumption of quantum computing. So you see threefold. Raising the awareness of the topic. Second is making people work together. And the third is standardizing things. And to do that, we organize a workshop every year. The next one is in Barcelona, which is a nice place, in May. The last one was in Grenoble in France, and the previous one was in Singapore in 23. But it's a long-term goal. It takes time to have people work together, agreed on the metrics, agreed on the benchmarking. There's also benchmarking initiatives in Europe on how do you measure the energy of a system. I'm working on a paper right now on the challenges of energetic challenges of FTQC. It's a paper that's going to be written by 6 people, a mix of academic and industry and people like me. That's where we are. It takes time. Raising awareness at the government level as well. So we did that in France. We are doing that at the EU level. And there's another element which we brought last year, which is that caring about the energy consumption or the power consumption of FTQC system is one of the key to drive a sizable market. Because if quantum computers consume too much power in line or in excess of what we have in classical supercomputing systems, it will prevent the quantum computing industry to create a sizable market because the machines are going to be too expensive. And the grid, the drain of the electricity grid is going to be too high, particularly for scientific computing. So our message is to say, if the industry both at the academic, the startup scene, and even the policymaking scene, want to create a sizable industry with quantum computing, we need to care about that. And we need to make sure that we optimize those systems so that they consume less than the largest supercomputing systems. Otherwise, the market is going to be too small. So it's an economical message.
What fascinates me is that if you think about the unit of compute per marginal unit of electricity consumed for quantum, if you're able to scale exponential, but your energy usage remain linear,
it's not that simple. It's not that simple. It's not simple. The cost of error correction may be high. It's a very good economical discussion that I'm starting to have with many stakeholders. I've got a big chart explaining that. I did present that in the US at the Santa Clara Q2B conference in December. Even though a quantum computer may bring a lot of value in chemical simulation, optimization, financial portfolio optimization, whatever, if the power of those systems is too high, it's going to be too expensive, whatever the value. Mm-hmm. So you can't afford having a system costing 200 megawatts of power. It's too expensive.
Why is that? Because now with AI, they're building 1 gigawatt systems of
yes.
That's not really.
You're right.
So why are you worried then about 100 megawatts?
Because there's a big difference between the gigawatt AI centers and the difference is how many users do you have. The gigawatt data centers are built to serve hundreds of millions of users. It's a mass market. It's driving actual value for millions of users. When in quantum computing, we are talking about a back-end system that is not serving hundreds of millions of users. Yeah. It's serving one user who's doing a chemical simulation to solve molecular chemical simulation to drive the creation of a new drug or whatever. It may be a financial portfolio optimization for a bank that will maybe then serve thousands of users. Usually it's a zero-sum game, I would say, in financial optimization, but whatever. So the market is not the same size. The value is not at the same location. So my comparables are scientific computing stuff. So if you look at chemical simulation, which is one of the sweet spots of quantum computing, the comparable is scientific computing. So I look at how many scientific computers are being deployed with how much power. So I can give you the number. How many scientific computers are deployed in the world which are consuming more than 10 megawatts? You know the number? How many of them?
I don't know.
It's less.
1,000?
It's 10.
Oh, wow.
In the world. So PsyQuantum, with their system that costs between 1 and 200 megawatts, they're targeting a market of less than 10. If you do comparables. So what they will say, they may be right. They say, oh, but my system is going to bring much more value than El Capitan and Aurora and Frontier Systems in the US and the DOE. Maybe, okay. But who can pay for that? Not many folks. Because right now, only fewer than 10 organizations in the world, mostly public organizations, can pay for more than 10 megawatts. Only 10.
And what is that?
Because it's scientific computing, it's not commercial AI. Commercial AI is a big bucket. But quantum computing is not address that market. Quantum computing is not replace the NVIDIA gigawatt data centers that serve hundreds of millions of users. It's not for the same market. So the market is different, the use case is different. That's why caring about the energetic cost of those systems is important, because otherwise you will have only a market of 10 or maybe 50. But if, that's where the energy comes in, if quantum computers, FTQC quantum computers are optimized to consume less than 1 megawatt or even less than 1/10 of a megawatt, then the market is going to be much larger. Even for scientific computing. Then the market is going to be a corporate market, a larger cloud market, and then maybe the market is going to be hundreds or even thousands of systems.
But is your assumption that the energy is too expensive? Is that one correct? Because typically when you got really breakthroughs in tectonic shifts, those also tend to happen with changes in energy. So for example,
the problem is the grid. The grid is not extensible like with a click. You need to produce the energy. I can give you a comparable, which is CERN.
If you look at the Industrial Revolution, energy moved down quite significantly.
Yeah, energy is cheap right now, even with a mix of nuclear, renewables, and fossil.
Is it not possible that in 10 years' time that we can see a significant step down of energy cost?
In 10 years?
Yeah, or 20.
I don't believe. In 10 years, no. People believe on fusion, nuclear fusion, but nuclear fusion is farther down the road than even FTQC quantum computers. So don't bet on fusion to bring cheap energy. And fusion is going to be expensive, at least at the beginning, when you see the capex at ITER and other places. So I don't believe in fusion. So what you can believe in is a cheap fossil energy. So you know what the companies like XAI and OpenAI are doing in the US. In some places, Microsoft and Google, they have kind of renewable powered data centers. But in most places, what they want to use to have cheap and fast energy is they use kerosene, so the fuel for airplanes, feeding turbines, which are similar to the ones in planes, just to get cheap and fast energy. But it's driving CO2 emissions, of course. It's very bad energy.
I was thinking, I'm also looking at Corning. And Corning is studying glasses, and they say, okay, they bought in 2000, they bought solar cells. And they said, okay, it's basically transmitting photons and glass and certain chemicals. And they said, okay, 80% of the photons are lost in that transmission. and so
you can prove that. You can improve that for sure.
Would it be possible to improve it? And maybe can you improve that with quantum technology?
Oh, with simulation, you mean?
Yes.
Maybe, yeah. It's probably. I mean, that's why. I mean, scientific computing using quantum computers can simulate matter, light-matter interaction in many different fields. Maybe yes, here as well. And then you manufacture your end product classically. That's what Corning may be. Okay, I'm sure any chemical company or materials company will be interested in using a quantum computer when it's available, of course. But it has to have a reasonable.
But it has to have down the cost price down of
electricity. Yeah, but it has to have a reasonable cost, because you can invest in new computing facility wherever you are, whoever you are, but it has to be reasonable. I mean, the IT budget are not extensive at will. If you look at the public data centers like HPC in Europe or DOE in the US, they can't expand that because the value is going to be deferred. The value it brings is deferred. So it is public money in most cases. When it's a commercial company, an industry company, they have a fixed IT budget. So usually, if you spend more in a given technology, it's at the expense of some other technology. But we know that when we will deploy quantum computers, it's not going to be a replacement of existing legacy supercomputers, because you will still need supercomputers to feed the new quantum computers. For example, if you do a chemical simulation with an FTQC system with thousands of logical qubits, you will need a classical system to prepare the simulation. And this is going to be a costly classical computing. There are three costly things that I want to evaluate as part of the QEI. The three costly classical tasks are creating the circuit itself, which may be complicated for chemical simulation, compiling the circuit with billions, if not trillions of gates. It's going to be very expensive. We don't know yet the cost of that. It may be affordable, but we don't know yet. And then managing error correction at scale. And error correction is going to be costly as well. You need DGX from NVIDIA in racks just to do that. I mean, even if we succeed in developing FTQC quantum computers, we need a lot of classical resources to drive them. So it's going to have an incurred cost. The cost is classical. The cost is classical cryogenics, classical electronics, and classical computing to drive those systems. So it's going to be costly. So we're going to make sure that it scales, it works, it brings value. We're going to have to invent new algorithms, particularly in optimization and machine learning. Otherwise, it's going to be only chemical simulations and material simulations. And there's a lot of interdependency between all these things to size the market. So energy, I'm focusing on energy as part of the QI. It's not the only element. I mean, it's one of the elements to drive a sizable market on top of finding good algorithms in multiple dimensions. So it's on top of building the software stack, the middleware. There are many elements that we need to build the value chain in computing, and energy is just one of them. Of course, it's not the only one.
Okay. Olivier?
The last one I would say on energy is, I've been working on that for nearly 7 years now, looking at this topic with Alexia Ofeb, Robert Whitney, the co-founders of QAI. What I found out is looking at the energy and the power consumption is a way to adopt a system-level approach when building those systems. So it forces engineers and physicists to adopt a kind of what we call a holistic view of the system, looking at the interdependency between all the components at the quantum physics level, quantum thermodynamic level, at the qubit control level, at the cryogenics level, at the software level, the middleware level, the error correction level. Everything is connected. And I think it's part of what we need in the quantum industry. We need to build a new discipline which is called quantum engineering. By the way, there was a conference in Paris. Where I met, by the way, people from TNO who are talking as keynote speakers as me in Paris. It's Quest IS. It's a conference on quantum engineering. Quantum engineering is a new discipline where you build out system integration approach with integrating the science, the technology to create product that delivers some benefit based on some goals, and you have to fix a lot of scientific and engineering problems, and this is quantum engineering. And it's a new discipline. It's being built. I mean, it's not well formatted yet. It's getting out of physics and building the engineering, but still doing physics. You need still a lot of physics to build those systems, and there's a lot of research going on there in physics. I believe in the role of fundamental research in quantum physics, but we need engineering on top of that to assemble very complicated systems with different parts, different trade-offs, different optimizations, different goals. And so you need a mix of science and engineering to build those systems. That's a strong belief I have.
Okay.
Because it's one of the new deep tech domains with a lot of ramification. And we talk a lot about computing, but in quantum tech, there's also sensing, communication, and another one which is under-evaluated, which is called quantum matter. And there are not many investors in that space. Quantum matter is a new field in town. Quantum matter is about designing new materials which have quantum effects. You can put quantum batteries in that field. You can put new materials being designed with quantum physics. It's a new field to explore. And I believe that quantum physics overall is going to help develop new domains, even in classical computing, even in classical domains. So you have to explore that deep tech as part of AI, as part of other fields, even classical semiconductor. It's something you have to explore. There's so much buzz around it that you need to be educated on what are the pros and cons and what are the technology potential there. So you need to be educated. You need to invest in some good companies there.